Hi, my name is Matthew Thomas. This is a general robot overview video. Um, we're also going to mention how other people can help us out with with building this robot if they want to. We're also going to mention stuff like what game strategy this robot's built for. We're going to go through every mechanism of the robot, and we're also going to go through like some things that programming should know about this robot and a few other mechanical things about how we do stuff. We're making this video because um, today we used up a lot of time in a meeting about how we weren't open enough with the CAD process, and that it seemed like only a few people were doing it. So that wasted valuable machining time. So hopefully this video solves that. Hopefully. Okay, so this is the robot. This is one of the. This is decently current, um, as current as I currently have it. I'm sure other people have their own, or other people that's also designing this have more updated intake, because I'm not doing the intake and feeder systems. But this is a pretty current robot. Okay, let's start where all robots start is the drivetrain. So a few specs is that this drivetrain is 26 inches by 24 inches. The 26-inch dimension is this way, 24 is that way. So it's 2 inches longer than it is wide. We know from past experience that longer robots are much easier to drive than, I guess, wider robots, like widthways this way. I don't know the physics behind that, but you can ask somebody smarter than me why that's easier. We're using four 6-inch Omni wheels. The reason why we're using Omni wheels is because we want to get around defense really well. So as opposed to traction wheels, Omni wheels allow you to like glide off of defense robots, while traction wheels, a lot of times you get into what's called a friction pin. You guys can look that up on Google. And also, Omni wheels are pretty fun to drive around. You drift everywhere, which is pretty cool. To power it, we're using 4 of the new Falcon 500 motors, and we're just using this pretty standard gearbox. Something cool that we're doing this year is we're doing a chain and tube system. So the way we're powering this wheel is actually using a chain that's hidden inside of the tube. Imagine that, it's pretty cool. The reason I'm doing that is because if we had to put the chain on the outside, that would eat up valuable robot space on the inside, which we don't want to do. Oops. How do I get that back? There we go. Okay, that is the drivetrain. I'll talk more about each individual component a little bit later, but this video is going to be pretty long. So let's go on to next thing the robot needs, which is an electronics panel. This is like the simplest electronics panel that I've ever designed, because we're using Falcons. You don't need what are called motor controllers with them. They're built into the Falcons. So we have a very small and elegant electronics panel, I would say. Yeah, there's nothing much to it. It's just a 16th inch piece of aluminum sheet with a bunch of electronics that Tasif designed. So, pretty simple. Okay, moving on. Where should we go next? Let's go shooter. Okay, so this is the shooter that we are going to use to shoot balls. Oh, I should also mention that all these designs are definitely going to change. None of these is finalized anyway. Okay, this is a shooter. What it does is it's also powered by 2 Falcon 500s. Then we have a big flywheel right here. So what a flywheel is basically a mass that turns super, super fast. So this is a 4-inch wheel, and it's going to be spinning at around 12,000 RPM maximum. And if you do 4 times pi, which gives you circumference, then you multiply that by 12,000 RPM, you can figure out how fast the exit velocity of the ball will be. That's pretty cool. Okay, so that's how we plan to shoot stuff. Here we go. Let's do climber next. Okay, this is the climber. So this is also powered by a Falcon 500, Anybody noticing a pattern? I sure do. Oh, I'm gonna cry at my jokes later. Okay. Um, so the way this works is that we have an inner stage here and an outer stage of tubes. And all of these are bearings. So we have bearings everywhere that fully support this tube on every direction and make sure that whenever it slides up and down, it's super smooth. So how we're currently planning to do it is that, oops, that's way too high. We raise this thing up, we hook on this thing to the bar handle. I don't know what the official name is. You know what I'm talking about. And we do that. It's powered by these two really long runs of chain that go up to it. Yeah, that's how the climber works. And then this is something we saw from Team Capital Robot in 3 days. It allows us to like move our robot when we're on the bar, so we could weight balance another robot that's also hanging with us. And that's powered by 1775 with a 180-degree reverse gearbox. You can look that up if you want more information. And that powers that. This thing is like completely prototype CAD. It's just to get all the, like, make sure it fits with everything else. Like, it has unfilleted corners. That's how you know it's not in any way, shape, or form done. Okay, moving on. Next we have let's do intake, if I can find it. Okay, never mind. We're still gonna do intake. Oh, here it is. Isolate. Maybe. Okay, never mind. Okay, so this is the intake. The intake's job is to bring game objects into our robot. Pretty cool. It starts inside of our robot frame perimeter, like so, and it extends using these drawer slides right here that we bought from Amazon. They're just like the drawer slides that you have in drawers and whatever. So this thing slides on it. It doesn't move in my model because someone else designed it. But so it moves out. Our current plan is to spring load it out. But that seems like a really bad plan, so we'll probably have to come up with something later. So it spring loads out to about like right here, and then we have these basically this row of wheels, and its job is to center and pick up the ball. So these are Mecanum wheels. Look up more about how they work if you want to know, but they can center the ball, and this middle one brings it in, and then that's also powered by a Falcon 500, which would go right here. Okay, next is feeder. That's this tall structure that does exactly what it sounds like. It feeds balls into the shooter, which is mounted up here. So the feeder is also powered by a Falcon 500. That goes right here, and it just uses this big wheel and these two like conveyor belt type things to send the balls up into the shooter. So the path the ball takes is it starts here, goes to here, goes up to there, and boom, we fire and score. Yep, level 3, nice. Let me think. Okay, for general robot overview, I think that's it. One more thing, battery probably mounts here, or down here. We haven't really decided on that yet. Depends on center of gravity calculations, but basically, that's overview of the robot. Now, I'm going to go talk about some other more specific stuff. I have a list. This video is going to be long. I'm sorry for that. Let's see what we're at right now. We're at 9 minutes. Oh, perfect. Okay. Let's talk about the drivetrain and more specifics of it. And let's talk about the general manufacturing concept that we have. That we currently have, I should say. So last year we made most of our robot out of bent sheet metal. So that's when we had a sheet of metal and we bent it. We couldn't do that in-house. Like, we couldn't do that ourselves, so we sent it off to machine shop, and we got the bent sheet metal back. That's how we designed most of the stuff we did last year. Um, this year we have a new design philosophy, which utilizes our new CNC router that we got, and it is basically what we have is we have tubes of aluminum. So these are aluminum tubes. They're hollow, like that, and we have metal gussets. So we machine the aluminum tubes on the CNC, and we plasma cut these gussets, and it's all made out of aluminum. What that's really nice because we can manufacture everything by ourselves. So our turnaround times from concept to built model is significantly lower than if we were to send it out and have somebody else do it. So yep, that's our design philosophy this season at least. I don't know what fun new toys we're going to get in the future season, so that might change. Let's talk a lot more about specifics of the drivetrain. So I'm going to pull up a few calculators. So this is the calculator we use to determine what speed we want our drivetrain to go at. It looks complicated when you first see it, but it's actually pretty simple. All it is that we input a motor. So you can see that the Falcon is selected, and we just input the speed and torque that motor has, and a few other things, and we put in how many of the motors we have and the weight of the robot, and we can try out different gear ratios right here, and that tells us not only what our speed of the drivetrain will be, this is in maximum velocity, but also what the sprint distance is going to be. When talking about sprint distance, it's basically like a cycle. So if I want to go from the like one side of the field to the other, that would be 52 feet, I think. I don't know how long the field is, but we could measure how long that would take with different drivetrains. So what we want to do is we want to optimize our drivetrain for a certain sprint distance, because the faster your drivetrain is, the slower it will accelerate. And you guys can Google that if you want to learn more about the physics behind that. But this is the drivetrain we chose. So it's optimized for a sprint distance of 20 feet. As in, we want to pick up balls from one side of the field, go over the bumps in the middle, and immediately shoot after that. We don't really want to go up against the wall of the goals, because that takes longer. So this is and this graph just visually shows you what it's doing. So you can see that at the beginning, this is time lower here, and this is distance and other things. So you can see at the beginning, our acceleration is essentially constant. That means our motors are basically running full power, and we can constantly accelerate the drivetrain. And then you can see we slowly start to get lower, or not slowly, we take a pretty big dip in acceleration once we hit maximum RPM of the motor. That's the maximum speed the motor can go at. Another way to show this is the velocity curve, which is right here. That's just a way to see it. So what we do is that we mess around with different gear ratios. So this is what a 10, we made it 2 times faster, or no, 2 times slower, and you can see the acceleration curve looks all messed up. It's all bad things happen to it, and we definitely don't want that to happen. So that's what we do to figure out what drivetrain speed we want. Okay. Next thing, let's see, what's next on my list to talk about? Oh, let's talk about programming, because this robot is pretty complicated, so we need good programming to make it work well. Pretty obvious. We need to know what sensors we should put everywhere, because it's very useful if we had them before we built the robot rather than afterwards. So, some options for sensors that I think might be good to have is we might want to have 4 or 5 distance sensors to detect when we have balls um, in what stage of the feeder. Um, all the uh, all the mechanisms have falcons except for this thing, and all the falcons have integrated encoders, which are so we don't have to worry about that. Um, we definitely need we probably want an IMU to measure the angle that the robot's currently at. That would probably be pretty important. Um, and then, like, what other, yeah. Oh, we also probably want a limelight. A limelight's definitely a must. So, tell us what sensors you want, and we will CAD them in, hopefully. Um, okay, moving on. Let's talk about how you can help. Like, say you're interested in CAD and all this design stuff, but you don't know really where to start or how to help stuff. Um, I know there are great tutorials on YouTube about how to learn CAD. Um, I personally use Fusion 360, and almost everybody else uses SolidWorks. Um, Fusion's probably easier to learn, but if you want to be like everyone else and use SolidWorks, that's totally fine too. Um, this CAD model needs a lot of work, so if you want to do something, right, in CAD, I'll have this model. This model is always updated, and I'll put a link wherever this video gets uploaded on the full CAD. So some things that we need, if you want to work on something, is we need a limelight mount for the shooter. We need a good battery mount. We don't have that right now. We need a actual version of this wheel pusher thing, because this one just looks pretty stupid. We need a few turnbuckle mounts. We need tons of other mount things. Like, you just ask me what's something I can work on, I'll tell you that this is what our robot needs. Okay, moving on from that, let's go into more specific design choices that we made for these different mechanisms, and the pros and cons of each of them. So, let's talk about, we already really talked about the drivetrain. The drivetrain's not very fun. Electronics not fun. Let's talk about the shooter. The shooter's pretty cool. So, this shooter was made to be extremely fast to assemble, and basically made to be fast to assemble. So what it's made out of is that, or not what it's made out of. Basically, the main mechanisms, the main parts of it is that we have this huge 3D printed hood in the back, and this thing's printed on one of our Prusa printers that we have, which is really cool. And then we have this piece of tube stock in the front that's going to be welded to these tube stock, or these aluminum sheets on each other side. That creates a really rigid structure for the super fast spinning wheel to go on. We also 3D printed these gears on the on our Markforged printers, and these gears allowed us to get a custom gear ratio with which we wouldn't be able to achieve otherwise. So yeah, that's how the shooter is done. I should actually show something else for the climber. Okay, so for the climber, how the climber works is that we utilize once again, a Falcon 500 put to a one-stage versaplanetary mount, and that goes to a sprocket down here, that goes to a sprocket down here, and this axle is connected to the two main sprockets that drive the elevator up and down. The key eye of, I don't know what I'm saying, it's pretty late, but a lot of people might be wondering, how does this elevator hold a robot up? Because at the end of the match, we still have to be holding ourselves up, and we can't tap any power to the motors. So how do we hold us up? And we have this mechanism on the side here, which also needs probably a few more redesigns before we actually build it, because it looks not very strong at this point. So what this is this is a ratchet, like a ratchet wrench, but bigger and adjustable. So what happens is that this thing spins on the axle that these two sprockets are on, and then during most of the match we have this little bar thing up, and that's just powered by a servo in the back. And then when we want to, when we get to a good height and want to hold ourselves there, we put this into this, and now we're locked into place. At least one direction. We can't go up anymore, but we can still go down. And so up and down is kind of reversed from normal thinking. So we don't want to be able to go up because that would actually lower our robot. But we still want to be able to go down because that would actually climb our robot higher, if you kind of think about it. It's confusing. So that's how that works. This entire thing is made out of the same tubes, which are, again, machined on our CNC, which is really cool. And then we use these, we have bearings in every single direction to support the tubes going up. So no matter which direction the load is in, the tubes will spin really easily because they're on the bearings. And then this red stuff is the chain. The chain is connected to this thing at this point. If anybody wants to figure out a better chain attachment method, that would be cool. Because right now all we're doing is taking a 16th inch plate and bolting it as hard as possible to the tube, and hopefully the chain stays in there. Other teams have done it before. It'll probably work, but better solution is wanted. And then, so that's the climber. Also in the climber, we have support for the outer rails. We have a piece of tube stock here, and we have a piece of tube stock slotted in between the chain, which is pretty cool. In the back, up top here. Let's talk more specifically about this wheel balancer thing. So, as you might notice, this is not mounted at the top of the robot. Some of you might ask why, because that would give us maximum extension. And the reason is because right above the handle where you hang on, there is a aluminum tube. And this is made to be in contact with that aluminum tube right above the handle. So our robot doesn't swing forwards and backwards, because the robot's center of gravity is somewhere around this point down here. So if we try to climb from the back, our robot would just swing forward and we wouldn't be able to climb. So that's what this top piece does. It holds us there, while this piece lets us ride along the handle. And this is just a few Coulson wheels, and then we have a chain running through all of them. Also, this entire thing can spin too. Yeah, this was made literally just a few minutes ago, so definitely needs improvement. Let's talk about some more things about how this is built. So these tubes attach to these tubes using welds across all this stuff. Usually I like to avoid welds as much as possible, because once you weld something, it's kind of difficult to unweld it, unlike a bolt. But in this case, it was necessary because we wanted to get the distance between these tubes as short as possible to put the least amount of leverage on these bolts. Because if you think about when this is raised up super high, right, and we're hanging off of this, there's going to be a lot of force on these bearings. And if these tubes are like out here, the leverage would be exponentially increased. which would be very bad, so we want to get the distance as close as possible. And that's what we have done. Okay, for the intake is pretty cool. So the intake we know is going to get hit by a lot of robots. Our drivers are probably going to run into a wall all the time, which we want the intake to be able to handle that, no problem. So instead of having just the whole row of wheels and rollers, and by the way, these rollers are 3D printed, so not very strong. We decided to put a huge aluminum tube right in the middle. So this is a huge tube that essentially allows us to run into anything, and the row of rollers are fully protected, which is pretty cool. This tube is connected to these aluminum sheets, aluminum plates by weld, which are then connected to these tubes, which are not aluminum. They're made out of a material called polycarbonate. And what's cool about polycarbonate is that its impact resistance is insanely high. So you could literally take a hammer, a baseball bat, or whatever, you could smack a piece of polycarbonate a million times, it would do nothing to it. While for aluminum and steel and stuff like that, it would deform it. So that's why we use polycarbonate here. We should probably color it so it's easier to see, but do that later. So that's why we use polycarbonate there. We like to use polycarbonate whenever possible because I don't know, I just like it a lot better than aluminum. So yeah. So the way this thing extends is it uses drawer slides. I think I said that before, but whatever. So we have a drawer slide mounted here and mounted on the bottom. So the drawer slides, the reason I have two on each side, and they're mounted perpendicular from each other. I think that's the word. Somebody's probably going to correct me if I'm wrong. But they're mounted perpendicular from each other is because drawer slides are only strong in one direction. So this drawer slide mounted here would be really strong up, down. While this drawer slide here would be really strong left, right. And that's just how they're made. So if we have two of them, now we're really strong up, down, and left, right, which is really cool. So that means we can get hit from the side, no problem. And yeah, that's why we use drawer slides. And these are like 200-pound drawer slides. Like, their load rating is 200 pounds. They're not physically 200 pounds. That would be pretty heavy. Okay, we're nearing 30 minutes, which is what I wanted to keep this video under. So I'm going to talk a few more things, then wrap up. Let's see. So the intake, the way we currently have it being pushed out is just a rubber band. And that method of pushing it out is no bueno. It would be really cool if we had another method of doing that. But we haven't really figured out anything that was better so far. And we want something where when we hit the wall, the intake comes in. So the rubber bands allow that. Rather, if we had like a piston or something that pushes it out and we hit a wall, it's probably just going to break the piston, which we don't want. Okay, let's talk about some other things. Oh, let's talk about center of gravity, because that's probably going to be a big topic later on in the season. So yes, our center of gravity is decently high. And the reason that is because we wanted to make a climber that could, a really solid climber that's really stable, and we wanted a really tall shooter to get around defense bots. So that naturally puts our center of gravity decently high, and with a high center of gravity, going over those steel beams in the middle might be a little bit of a problem. But since we have 4 wheels, it'll be better than if we had 6 wheels. And as long as we don't go over them too fast, we shouldn't have any major tipping issues. Let's see, what other things I wanted to say. Okay, I'm just going to wrap up. Okay, I'll have a link to this whole CAD thing. The CAD is automatically updating, so whenever I save a new version, the link gets updated too. So whatever link is there, that will be the most updated version. If you see this now in a week or in a few years, it will be the most updated version. If you have any questions, you can go ahead and ask them. Please put them in I think it's called a thread, something like that. If you want to help out, download the CAD model, make a mount for a Limelight or one of the other things I talked about. That would be super cool. Other ways to help out is making order lists. Like all the parts that we need for this robot is pretty big pain, putting them all into one list. We also have like cut lists and different things, like different managing tasks. If people wanted to help out in those ways. Okay, well, I think that's where I'm going to end it. It's getting late. Goodbye.